Good afternoon, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Network Intelligence at the Robert Bosch Center for Cyber Physical Systems, IISc. Today's talk is by Professor Abhishek Sinha, and he will be speaking on K-experts, online policies, and fundamental limits. Professor Abhishek Sinha is currently a faculty member in the School of Technology and Computer Science at the Tata Institute of Fundamental Research, Mumbai. Prior to joining TIFR, he had been on the faculty of the Department of Electrical Engineering at the Indian Institute of Technology, Madras. He received his PhD from the Massachusetts Institute of Technology, where he was affiliated with the Laboratory for Information and Decision Systems. Thereafter, he worked as a senior engineer at Qualcomm Research, San Diego, in the 5G standardization group. He obtained his ME degree in telecommunication engineering from the Indian Institute of Science, Bangalore, and BE degree in electronics and telecommunication engineering from Jadavpur University, Kolkata. He is a recipient of the INSA Medal for Young Scientists 2021, Best Paper Awards in Infocom 2018 and MobiHawk 2016, and Jagdish Bose National Science Talent Search Scholarship, Kolkata. His areas of interest include theoretical machine learning, networks, and information theory. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I'll be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Professor Sinha directly. Over to you, Professor Sinha.
Thanks a lot for the invitation to give a seminar here, and welcome everyone. So today we'll be talking about this problem on K-experts, online policies and fundamental limits. This is a joint work with my students, Shodav Shahu, who is from IIT Madras, Atif Joshi from TIFR, and my former postdoc, Shamrat Mukhopadhyay from ISM Dhanbad. So part of the work appeared in this year in AI Stats 2022, and part of this work is going to appear in ITW 2022 in this year. All right, so we'll be considering online learning problems. So here is a typical canonical example of online learning problem. So let's say at every morning you'd like to commute from your home to your office, and there are and you drive there, and there are multiple routes you can actually choose at every day. So the problem is which route you are going to choose for the particular day. So of course you would like to minimize some cost, let's say delay, or you would like to avoid the condition. But the information on each path is online, so you only get to know the past history, but you don't know what is going to happen for that particular day. So the problem is how to choose a daily route that minimizes some objective metric. For example, minimizing the total travel time over let's say 1 month or 1 year or something like that. So this is a very canonical problem. This is known as online short expert problem, and there are multiple variations of this. Consider another problem. So this is the display ad problem. Yeah. So let's say you're running an ad exchange, and so ad exchange, it does what? So let's say whenever a new customer comes, there is an opportunity for you to display ads. You have a pool of n ads, but given the limited slots that you have, you can only display a subset of ads. So let's say k ads. Now the question is which, and you get a reward if the user clicks any of these ads that you display, right? So this is a very canonical problem. This is a display ad problem. So your problem is how do you actually learn what is the most beneficial set of k ads that you display for a particular user when you are presented with their some demographic information or some side information for the user. So based on the past data, how do you decide which set of key ads to display? So this is again an online learning problem, and we will be considering these sort of problems in this talk. So a very general way and a very classical way to model this sort of problems is known as the prediction with experts advice framework. So I'm going to describe this classical framework first. So in this framework, so you can model this problem as follows. So let's say there are n experts, right? And each of these n experts are predicting on the outcome of a sequence of events for t rounds, right? And so there's a learner, and the learner's job is to select for every round one of these experts, and the learner can randomize which experts to choose from the given pool. And it can actually learn over time, and it can accordingly it can choose, it can make its decision for every slot. So whenever the learner selects the expert I receives a reward of RTI, which is I'm assuming that this reward is bounded between 0 and 1, or it incurs a loss, equivalently incurs a loss of LTI equal to 1 minus RTI at the round t. But of course, these rewards or losses are revealed to the learner only after the end of this round, right? So the question is, what is a best expert selection strategy that maximizes the total cumulative rewards accrued by the experts, by the experts selected by the learner? So a very classical metric to optimize is called the regret metric, where so in the reward version we simply compare the reward obtained by the learning policy, that's the second term in this equation number 1, versus the reward obtained by the best expert in hindsight. So when you are revealed all the rewards of all the experts, and you are what are the rewards obtained accrued for a particular expert for a given expert I, and you simply choose the one, the best static expert, which accrues the most reward in hindsight. So this is known as a regret metric, this difference. And an objective for this learning objective is to minimize this regret, and I will to show some bounds that so it achieves the fundamental bound that is possible, that is achieved. So we will be talking about this problem, but this is objective metric, the classical objective that this learning policy, online learning policies try to minimize. Okay. And so what kind of algorithms are good for this problem? So one canonical algorithm is known as a Hedge algorithm. So imagine this, given so what is a greedy policy? A greedy policy simply looks at the set of the total cumulative rewards that is obtained by each of these experts up to round t, and simply a greedy policy might simply greedily choose the expert that is having the highest cumulative reward up to the current time. But since the rewards are kind of decided by the adversary, the greedy policy can be shown that it receives order t, linear regret. So a very simple variation of this greedy policy, so instead of just selecting the expert having the highest cumulative reward up to time t, this Hedge policy simply it is a probabilistic policy, it is a randomized policy, and it places a probability mass according to the cumulative reward obtained by each of these experts. So it is not going with the best expert in hindsight, the best expert that is seen up time t, but simply it just assigns a probability mass which is proportional to this exponential of eta times rt minus 1I. So this is a cumulative reward obtained by expert I up to time t minus 1. So eta is simply a learning rate which is assumed to be constant for now, right? So this is and it can be shown that this policy, unlike the greedy policy, that is a sublinear regret, and the regret bound is shown in the final line. So this regret is simply upper bounded by square root of 2 LT star log n. So n is the total number of experts, and LT star is the loss. I'm looking at let's say what is the total loss achieved by the smallest loss achieved by the best expert in hindsight. So it is LT star plus log n. So this is the regret achieved by the greedy policy.
Hello, Abhishek.
Yes,
I have a question.
Okay, yeah, sure.
Are not these RTs random?
Which RTs?
R of small t.
No, these are okay.
No, so, capital R of small t.
Capital R of small t.
So if you see
this is a cumulative reward,
you have
right?
used the expectation somewhere.
I'm used. Okay, I see.
Yeah,
so you mean this expectation of RT? Okay,
yeah.
so this expectation here, this is the expectation appeared in equation 1. This expectation is with respect to any randomization used by the learning policy. So there is as such there is no stochasticity associated with this the rewards. So the rewards are decided a priori by some adversary, and the rewards are fixed. These are only revealed to you as you go, but it assume that they are written somewhere. That is not revealed, that is simply revealed to you as you go. So there is no stochasticity associated with this small RTI, and this expectation is with respect to the any randomness associated with the learning policy.
Okay, thank you.
Right. Okay. All right. So this is the okay. So we have shown that what it's a very well-known classical regret bound, and this is achieved with Hedge policy. And Hedge policy also has this is called small loss bound, and it helps in certain if you look at the banded version of this problem, so it helps. But let's not go into that. So we're in the full information version of this problem where the losses are the rewards achieved by each of these experts at the end of this round, right? So you're only considering the full information version of this problem in this talk. All right.
So how does the bound depend on eta? Sorry.
So this is okay. So this bound is actually obtained. So this is kind of the best bound that you can obtain, and eta depends on. So you choose the optimal eta for in this case, right? So eta is actually tuned with the optimally to get this particular regret bound, and eta can be chosen again accordingly in an online fashion that gives you this particular regret bound. Yeah, so eta actually, so although I shown here the eta is to be constant, but eta is actually tuned. It needs to be tuned to get this to achieve this particular regret bound here. But if you assume that your horizontal length is known, or some upper bound to the the loss achieved with the best expert, you can actually set your eta accordingly. Okay. All right. So now, okay, so now let's so we actually come to the main topic in our talk. So this is the K experts. So what is the K experts problem? So this K experts, so far whatever we have described before, it's as a simply a classical experts problem. The K experts problem is a generalization of the classical experts problem, where at every round the learner, instead of selecting only one expert per round, it selects a subset of K experts. Instead of so in the classical case it selects only one expert, but now the learner can select a subset of K experts from the set of N experts at any given round. And the reward that is obtained by the learner is a function of the selected subset. So let's say the learner selects a subset of ST at round T, then the reward that it achieves is simply given by QT of ST, which is only revealed to the learner at the end of every round. Now there are various classes of rewards that you can consider. For example, sum reward. So it is simply in a modular function. It is a sum of different sum of RTI, where RTI is actually given by the it is given by some adversary, and you simply look at the cumulative sum of this the rewards in the sets S that you actually selected. Similarly, you can define max reward version, pairwise reward version, monotone reward version in general, right? So in general, we assume that there is some function that is revealed to you after an round, and these functions belong to a certain class that will actually characterize later. But these are some examples of 4 examples of classes that I have shown. And here our objective is against the same. So we just would like to minimize the regret. But recall that here, instead of looking at selecting only one expert, the offline policy can select a set of K experts. So in our definition of the benchmark, I'm looking at QT of S star. That is the best subset of K experts that maximizes the total cumulative reward obtained in hindsight, right? And here, similar to the previous case, here in the expectation is with respect to any randomization used by the learning policy, right? So my objective is to design an efficient learning policy that minimizes this regret or some version of this regret that I'll consider later, that will define later. Okay, so any question on the problem setup or the objective function that we'd like to minimize so far? So okay, so if you have no questions, so let me now go to some details.
Abhishek, okay. Can you hear me?
Yes. Yeah, sure.
Nilesh here, quick question. So these rewards are changing with time, is it?
Yeah.
But one has no idea of how they're evolving.
So for example, yes. So even consider the, let's say, classical, Hedge, classical experts problem. So they are also, the rewards are RTI. It's a function, it is determined at every round, changes with time. We are only going to assume that they are bounded between 0 and 1, but that's it.
Okay. But if there is no correlation across time, then
no correlation.
Then I mean.
So just compare it with this Hedge policy. So there is no correlation with time, and so it depends on the benchmark. So their benchmark is kind of naive. It stays the same all over the horizontal length. So we are only looking at what is the best reward achieved by the fixed benchmark. But here, your learning policy, they're free to choose any expert at every round. So kind of the benchmark is kind of at a disadvantage, but again, it is at an advantage because it sees all the rewards in hindsight. So here is this kind of tension. And the same thing applies to k-experts problem as well. So we are all, again, we are going to assume that all these RTIs are bounded and stuff. So they are all nice in between 0 and 1.
Thanks.
Okay. Right. Okay. Any other question? Okay. So let me now. Okay. So let's look at some of the application before we go to the algorithms, because so of course, so the prediction of k-set. So let's say you'd like to predict an unknown sequence, and we'll see that this problem is very much relevant to the caching problem. And but instead of predicting only a single number, so you'd like to, so there is a linearity sequence that is revealed to you as you go on in online fashion. But instead of predicting a single symbol for the next time period, what you are going to do, you are going to reveal a subset ST, and you are fine. So you get a reward of unity if the next symbol falls or it is included in the subset that you actually choose, right? So this is called the prediction of the k-sets problem. And of course, I mean, it can easily, casted in this framework of the k-experts. And online caching is a nice example of this prediction of k-sets problem. So here, just assume that you have got a cache of capacity k, and there is a library of n files. N is very much larger than k. Okay, so it should be cache of size k, right? And the user, and there is a user who may request. So this is a file request sequence that can request any file at a given round, and your reward is simply you get a reward of unity if you get a cache hit. Otherwise, you get 0 rewards. So it nicely fits. It's a linear reward function. But if you're looking at something more general, let's say online sparse regression. So what happens there? At every given round, the learner decides a sparse regressor vector. Let's say WT. Right, and this WT has only 0 everywhere except in k coordinates. So it only looks at, it needs to look at k coordinates of the given xt and yt. So this is the feature vector, and yt is the sort of the value of this feature vector. And the loss that you actually incur for that, for predicting this sort of regressor WT for the particular example x2 yt is simply given by the squared loss function yt minus the inner product of WT xt whole squared. So the question is again, how do you actually select the non-zero location of the WT vector, and how do you actually also select the values for this particular non-zero locations? So this is a very famous problem, this online sparse regression, that also falls into this framework. And I'm not going to describe the other examples. For example, online dictionary selection, subset selection, feature selection of in high dimensional data, and they also falls into this k-experts framework. So they can all be formulated into this framework. So this is a sort of very interesting class of problems, and it is also a non-trivial class of problems that can be nicely modeled in this framework. So okay, so these are some applications. So now let's look at how do you actually propose a solution for this problem. So a natural, since we already know like the Hedge policy in and out, so a natural approach is to know whether you can actually model this problem, this k-experts problem, as an instance of this experts problem, right? And it turns out that there is a very inefficient reduction of this k-experts problem to the standard experts problem. So let's see how I'm doing. So I'm doing good. Okay, so it's a very inefficient reduction. So what is this reduction? So you define n choose k meta experts. So for every subset of k experts, you define as a meta expert. We call it meta expert, and there are n choose k of them, of course. And you simply run the Hedge policy on this meta experts. Right? This can be done in principle, and it achieves the following regret bound. You just plug in the regret bound with n choose k, where a number of experts, and you get this regret bound. And this regret bound, it can be shown that this is tight, sort of tight, right? Or it is ordered optimal. But the main issue is that, of course, the complexity. So if you are actually running this with so many number of experts, which is exponential, if k is like order of n, it is super exponential in the number of n. This is totally impractical. So the question is, can we actually achieve the same sort of regret bound that's optimal, but making this the runtime even better? Can you, for example, we are looking at runtime which is kind of linear in n, but here this particular reduction is kind of exponential in n. So the question is whether we can actually achieve this thing, the best of the both worlds, small regret bound as well as the very good time complexity. Turns out that yes, and here is the key observation. The observation is that the reward, so you're only looking at, so for a randomized policy, you're looking at the sum. Let's say just consider the sum reward problem for now, right? So the property of the sum reward, if you just use the expectation, the linearity of the expectation, so expected value of q sum of t, it is the inner product of the particular reward vector RTI and the inclusion probability vectors. So the probability that a particular expert I is included in the subset. So this just follows from the linearity of expectation. So here this is observation. This means that the rewards, the expected reward doesn't depend on the whole probability vector, whole joint inclusion probability vector. It only depends on the marginal inclusion probabilities of individual experts, right? So in other words, let's say I have got two learning policies. These two learning policies might have two very different joint inclusion probability vectors for the experts. But if they agree on the same marginal inclusion probabilities, they have the same regret bound. In fact, they have the same performance in expectation, right? And we'll see that this observation, this is a very simple observation, and this holds only for linear rewards. So this definitely doesn't hold for non-linear rewards, and we'll be considering those rewards in a short while. But let's say right now we are just getting started with this linear rewards, and this is a very simple observation, and we'll see that. So okay, this is a key observation for making this algorithm efficient. So this is how it actually works. So we call this framework the SAGE meta algorithm. So this is not a single algorithm. There's a class of algorithms, and you can actually implement SAGE with the by defining different components. So yeah, here I'm going to define the components. So let's say we begin with any low regret base online prediction policy. For example, Hedge, right? We know that Hedge has a very good regret bound, but there's a very horrible complexity. Now what you do? For each round T, you efficiently compute the marginal inclusion probabilities induced by the base policy. Right? Somehow, let's say you compute it, the marginal inclusion probabilities for Hedge, let's say. And once you compute the marginal inclusion probabilities, use some other sampling technique for sampling the elements according to the marginal inclusion probabilities you just computed in the previous step. And again, it is a non-trivial problem. So how do you actually, sample, K items without replacement according to some probabilities that you just computed before? But assuming that you can do it, so step 1 and step 2, that's a computing the marginal inclusion probabilities P, and then sampling K elements without replacement according to the P, then the problem is solved. Assuming that you can solve both these two steps efficiently in time, right? Now we show that for this sum reward problem, both the problems can be solved in near linear time, and this is how it is done. So let's just use Hedge as a base policy, right? So in that case, if you know Hedge policy, Hedge simply we actually described it before. So for every subset S, we assign an expert, and PT of S is proportional to the exponential of the reward eta times the reward obtained by that particular subset of experts. Right, so PTES is proportional to WT minus 1s. The thing in the denominator is simply the normalization constant. Now it turns out that, so this is my joint inclusion probabilities for K experts. Now we need to compute the marginal inclusion probabilities. Now magically it turns out that if I just compute the marginal, the PTI, the thing that I shown in blue, it can be expressed in the following form. So PTI is simply proportional to WT minus 1 of I. WT minus 1 is simply exponential of eta times RTI multiplied by ek minus 1. This is a function. I'm going to tell you what this function is. WT minus 1 minus I divided by ek WT minus 1. Now this ek minus 1 and ek function, this is the pth order, the EP function is a pth order elementary symmetric polynomial, which is defined in the following. So it's simply you take all combination of this given any vector P, you just compute the product of all P subsets of size P, and you sum them up. So this is known as a elementary symmetric polynomial, and it is well known that ESPs of any order can be computed in log n time using fast Fourier transform. So this is a in a very well-known method for computing evaluating this elementary symmetric polynomial, which means that if I just from the formula of PTI, I know how to compute WT minus 1. It is just exponential term, and I can compute each of these two functions in near linear time. So that means my step 1 is solved. So I know how to evaluate the marginal inclusion probabilities for each of these elements in a very efficient, in almost near linear time, right? So the next step is how do you actually, okay, once I have computed, so I've got this vector of length n, PTI, which is computed very efficiently. Now the question is, how do you select a subset of k elements without replacement that satisfies the same marginal inclusion probabilities? And here we take inspiration. Actually, we don't take inspiration, actually use a very old technique that is used in survey sampling. And this is known as Meadows sampling. So what Meadows sampling does, Meadows sampling is an exact sampling procedure without replacement that given once you feed it any feasible inclusion probability vectors, which means some vector pt such that sum of pti is equal to k and all of these elements are non-negative between 0 and 1, then it outputs a randomized sample such that each of these elements I is included in the sample with probability pti. And I'm going to describe what this Meadows sampling is. It's a very nice and clean way of sampling. So here this is the algorithm. So let me just go through the algorithm first, and then I'll give you an example how it actually works. Okay. Okay, all right. So Meadows sampling scheme works like this. So you first, okay, so let me first give an example, then it will be easy to show. So just assume that, so I have to, select 4 elements from given 8 elements, right? And the corresponding probabilities are simply given by this pi I for this element I. Then you simply compute these quantities P1. So first you order the elements in any way you like, right? P1 to so 1 to 8, you just numbered them, and then you simply compute P1. P2 is computed P2 pi 2 plus P1. P3 is computed P2 plus pi 3. Pi 3 is the inclusion probabilities. So you get this demarcations P1, P2. You get these points on line, which is from 0 to 4. And then you toss a coin, but instead of tossing a coin, you basically sample uniformly distributed random variable. Let's call it U. And let's say this U falls somewhere here in between P1 and P2, right? And this is how the sampling works. So whenever U falls, so wherever whichever interval U falls, you just select the corresponding element, and then you keep incrementing U by 1. So first, let's say the U falls in between P1 and P2. So you select element number 2, then you increment U by 1, and let's say it falls between P4 and P5, which means you select 5, and then you again increment U by U plus 1 by 1, so U plus 2. It falls between P5 and P6, so you select element number 6, and ultimately you again increment U by by U plus 2 by 1, so you get U plus 3, and it falls between P7 and P8, and you select 8. Right? So this is how Meadows sampling works. And it can be, you can easily see that the probability that a particular element I is sampled is whenever this U falls in between pi j minus 1 and pi j, where pi j is a cumulative sum, right? And it is simply given by pj, right? So very simple, if you just think about it in 1 minute, you'll get it. Why it always, so it's an exact sampling procedure, and it solves the problem. So okay, so
Abhishek, one question. Do you mean U plus I here?
Yes, U plus I, yes, that's true, but there exists for a particular element of J, for this particular element, there will be only one I that will be feasible.
No, what I mean that pi j could be larger than 1, but U will always be between 0 and 1.
Oh yeah, sorry, yeah. So for there exists some I, yes, sorry, yeah, there exists, so U plus I lying in between pi j and pi j minus 1. Yeah, you are absolutely correct. Yes, this is what I meant.
Okay.
Yes, I'm sorry. Yeah, the picture is correct. There in the equation there is what U plus I. All right. Okay. So this means, okay, so we know how to solve this problem for the sum layered version. Now the interesting thing is that what happens to the general nonlinear rewards. So you simply can't play the same trick that you played before, because the linearity of reward doesn't work. Of course, it's a nonlinear function, so the expectation simply doesn't distribute over each of these individual elements. So we need to do something else. So how would you actually, approximate the function? Let's call it QTF, the reward function, with some sort of modular function. So you linearize it. Okay. So Okay, so let's say there is some way of linearizing it. I'll make it precise in what way you can actually linearize. And you actually, then you get QTS, you get the corresponding components QT of I, and you simply, run the same some linear reward policy on this QT of S. So here is the meta policy for this nonlinear rewards. You somehow find a modular approximation. Modular means a modular function is modular when a function f of s is simply given by the sum of the components, corresponding components for some function of that individual components. So find a modular approximation to the given monotone reward set function. So we are assuming that the set function is always monotone. So if you add more stuff, you get more value, right? That's a very natural assumption. And now consider a sum reward problem with the rewards given by the modular components. And then finally use Hedge policy for the resulting sum reward problem, right? So this is meta policy. Now we have to fill in the details. So how do you actually compute the modular approximation, and what kind of, more importantly, what kind of reward guarantees, what kind of regret guarantees this sort of algorithms can give you. And so here is I ask this question: so which nonlinear functions are probably learnable, and how to find a suitable modular approximation? Then we can actually use this meta policy, and this is where things gets very interesting. So first, I'm going to define a set of reward functions we called alpha-admissible reward. So it might look that way, I'm taking it out of the blue, but we'll see that it is very natural, and it has got some connection with game theory as well. So bear with me for this slide, and then I'll explain like why it is meaningful. So reward function f is called alpha-admissible for some constant alpha which is positive if there exists some real number g1 to gn. So these are like the modular components such that the following two classes or sets of inequalities work. So sum of gi over all I in S for every subset of S is upper bounded by some alpha times of f of S, right? For all subset S in N, right? There are 2 to the power n minus 1, 2 to the power n number of subsets, and for the full set, sum of gi is equal to fn. Okay, so any reward function that satisfies these two inequalities, these are known as alpha reward functions. And any there could be many such g functions. There could not be any. So for example, it could be empty. There doesn't exist any such g for which you can write it, or there could be many as well. So the set of all alpha admissibility, what is called the alpha code of A, right? This could be empty, or this could contain multiple values. So you can see that this alpha admissibility, what I have defined so far, so in principle, it can be checked by checking the feasibility of an exponentially large LP. So you are basically looking at the set of all feasible solution to this LP. So G's are your variables of this LP, and you are just looking at the feasibility. But now I'll show that this is a very natural class of reward functions.
Can I ask a question?
Yeah, sure.
Are the G's positive?
No, G's are not required to be positive, but you will see that G's will be positive for the class of reward functions that we'll consider. So in the next slide, it will be clear what G's are.
But
here we don't have, we don't make any assumption on G's.
Is the F monotone?
F is, you can assume F to be monotone. So because this is a reward function QT of S, and we assume that if we add more stuff to F, the value doesn't decrease. So F is monotone, the only constant. But again, it is not strictly required. But so you can assume, but for simplicity, you can assume that F to be monotone. That's it. Yeah, F is that's it. So this is only condition that we require. Okay. So as I said, so alpha admissible rewards have a succinct characterization that I'm going to show. And so here is this this punchline. So think about a cooperative game, and looking at the code of the game. So what is the code? The code is the set of imputation, or so let's say you have a cost sharing game, and you'd always like everybody to cooperate. So everybody, the grand coalitions to form. So what is the condition for the grand coalition to form? So this is a very classical concept in game theory, cooperative game theory. It is known as the code. And if you look at the definition, you will see that for the case of alpha equal to 1, our definition, the way we have defined this alpha admissibility, it simply coincides with the code of the function f of this. That means the game G and F, where f is a cost sharing game, right? But it is more general because I'm assuming I'm letting any alpha positive to be fine. But anyway, so that's why I call this set of rewards function to be alpha code. And so now in theorem 2, there is a classical theorem on what is a non-empty. So we are basically looking at functions with non-empty code and non-empty alpha code, and there is a classical result on game theory that gives you a necessary and sufficient condition such that a particular function has non-empty code, and this is known as the Bondareva-Shapley theorem. So here we simply generalize it. So this generalized Bondareva-Shapley theorem says under what conditions on function f this alpha code of a function is non-empty, and it is simply given by this, and this is simply, it is a one-liner proof. It's given by, you should just take the dual of the previous LP, exponential size LP, and this characterization gives you under what conditions on the function f the code is non-empty, so that you can find a set of g functions, vector g, that satisfies the above conditions, right? So this is a if and only if condition. Okay, fine. But how, how is this functions related? How are these functions related? So as you might have guessed, okay, so before you go there, so some examples of admissible functions. So alpha admissible functions, so submodular functions that are one admissible. So they are just, they just follows from the fact that submodular functions are in the alpha code, so in the one code. So this is a classical result in game theory by Shapley. And here you can find lots of functions in lots of vectors in this code. For example, the successive increment vector. So gi, if 1 to I minus f 1 to I minus 1, by just order these elements in any way you like, and let's say this function g, the function f is submodular. Then, as Professor Rajesh asked, then you can show that in the case of submodular functions, the gi is the successive differences, they are always they're non-negative. You can again show that, because it's a monotone non-decreasing function. And so this is one way of finding the code for submodular functions, right? And also it is known that Shapley value we can compute. So there is a concept in game theory. It is also in the code. It is basically the base of the code. But we actually go beyond the notion of submodularity. So we can look at some generalized definition of submodularity, which is alpha submodular functions, which is actually very much important for when you'd like to solve online sparse regression problem, because it can be shown that the function, the relevant function that you care about, it is not really submodular, but they're alpha submodular. So that's why we actually care about this alpha submodularity. And these functions are also G alpha admissible for some non-decreasing function G that can be explicitly characterized. And some non-submodular functions derived from certain martingales they are also one admissible. So there are many examples. The point is that we can go actually much beyond convexity, which is the relevant notion is submodularity here with this definition of this alpha code. All right. So okay. So we have actually characterized this set of functions that we actually admit. So we call it this admissible function. But what kind of guarantees we can actually derive? And what is the learning policy? The learning policy is problem that you have already guessed. So once you get a function ft, the reward function ft, you simply in your sum reward policy simply feed this any vector gt in the alpha code of ft. I'm assuming that the alpha code is non-empty and you can compute it efficiently. So in general, computing the code of any general reward function is an NP-hard problem. It's known, but assuming some structure, you can, let's say you can compute it, and you simply feed this vector gt to your sum reward function, sum reward online policy, which could be Hedge or which could be FTR, and this is how it goes, right? So we are just using the learning policy for the sum reward function with this modified form of linearized form of this function, non-linear functions, right? So now let's see what kind of regret guarantees one can give.
Just one clarification.
Yes.
If you could go 2 slides back to the characterization page.
Here.
So next one.
You mean this?
So alpha admissible. Does this? No, this is admissible rewards. No, you had something about the characterization, right? Where you define the.
Yes. You mean this thing, right? This is if and only if condition.
No, that is just LP duality.
LP duality, right?
Can you go a little to 18, I think, slide 18. Slide
18, okay, yes.
Maybe 17.
Oh, okay.
Sorry about this, yeah. So here, are you characterizing the set of alpha admissible functions?
No. Here, I'm just giving some examples. So I'm giving some exemplar functions which are alpha admissible for certain values of alpha, that's it.
Okay, so
for
for one
example, submodular
admissibility,
functions,
you have submodular. Okay.
submodulars, and you have alpha submodular. I have not defined what alpha submodulity means here. There are multiple definitions, but you assume that this is some weakening of the definition of submodularity.
Yeah, thank you.
Yeah.
Abhishek,
So these
I
are just
also
examples.
have a comment. So
Yeah.
when defining alpha admissible functions, you consider subsets of all cardinalities.
Yes,
Right?
absolutely.
But now that you are interested in K expert, if you consider only subsets of cardinality K, maybe you'll get a better alpha and a better bound.
Yes, you are absolutely right. You are absolutely right. So this is probably more than what you actually want.
Yeah.
But okay, so actually we did consider it, but we didn't find it any theoretical advantage. So we couldn't find any function which is alpha dash admissible or alpha admissible plus, which means you only consider, so in equation number 2 you only consider cardinality of S equal to K rather than considering all S subset of N. But strictly speaking, you're right, we only need a very weakening form of this. So we only need this equation to hold for cardinality if is equal to K, but it doesn't hurt if I just take all S.
Okay.
Right? Okay, so any question? Okay, so if no other question, then I'll just so I think this algorithm is clear. So you're just feeding these vectors to this summary word online policy, and now let's see what kind of regret guarantee, regret quote unquote, because we will be getting something different sort of guarantees for this function. So equation 4 follows from the summary word version of this problem. So the linear reward, I'm just considering the linear reward, and our policy, let's say Hedge or FTRL, guarantees the normal regret guarantee of order of square root t, right? And now let's use the definition of submodularity, alpha admissibility in equation number 5. So it says that expectation of ft of st, by definition, it is lower bounded by sum of this GTI, which is inner product of 1 over alpha times inner product of GT and PT, right? This by definition. And sum of ft of n, which is the reward accrued by taking all n experts at every round. It is simply sum of GTI over n. And again, the last property, this last inequality of or the equality of the alpha admissibility definition is simply given by, it is upper bounded by n over k, right? So over this max of p star in delta nk. Delta nk is a set of all p's such that sum of pi equal to k and all these p's. So this is the inclusion probability vectors, and the p's are in between 0 and 1. So this is simply upper bounded by n over k of this quantity that appears in the regret bound here in equation number 4. So if you just combine these two, so here is the guarantee that you actually get. So which means k over n alpha times sum over ftn, which is our kind of benchmark. And this is a very new benchmark in the sense it is not the best offline reward with k experts. It is the reward that you actually obtain if you are taking all the experts at every round, right? So there is nothing that you need to compute. So it is simply the maximum thing that you can get by taking everybody, all the experts at around n, but we are diminishing it by a factor of k over n alpha, right? And expect the second term is simply expectation of ft of st. It is simply the reward accrued by the online policy that takes only k experts at every round, and you show that this is upper bounded by order of square root of t. This simply follows from the previous regret bound, right? So here our benchmark is a little bit different. It's sort of it is, so it cannot be compared with the regret definition. So in some sense it is much more stronger, in the sense we are, instead of taking only k experts, the best k experts in hindsight, I'm actually taking the set of all n experts in hindsight. But again, and it is also weaker in the sense it is diminishing the reward obtained by that by this policy by a factor of a constant factor of k over n alpha, right? And this is a regret guarantee that you actually get, and we show that this is tight in the sense there exists a lower bound, and you can't do better than this sort of guarantees. So so k over n, so there exists a sequence of one admissible reward function such that for any online learning policy this is tight. So it is lower bounded by omega square root kt log n over k. So the kind of guarantees that you get is minimax optimal. right? So let me see how much time I have. Okay, 10 minutes, I think. Okay, so what I'm actually going to do, I'm just going to skip the proof ideas. So it's just a probabilistic way of for the lower bound is proven using a probabilistic method, which is the same the proof technique that is used by the great Shannon in proving his channel coding theorem. So if you're from information theory background, you already know how these things work, but there are some details that needs to be filled in. So I'm going to skip it. And what I'm actually going to do, I'm actually going to, kind of going into the second part of this talk. And I'm looking at this problem, which is the fundamental limit of online caching. And we'll see that this is very much related to the K-experts problem that we have been talking about earlier. So the setup is as follows. So although we have already defined what this cache is, so let me again define what is this problem. So you have a cache with capacity C, right? And this protocol evolves over a round of it runs over a length of t rounds, and this is how it first works. So there is a caching policy which first prefetches a subset of C files from remote server to this cache, and then a user requests a single file at every round. And the user, if the file is already in the cache, it gets the learning policy gets a reward of unity. Otherwise, it just gets the cache miss, right? And so you can immediately see that this is an instance of the K-experts problem where the files are the experts, right? Although, I mean, I'm okay using this notation C here, but it's actually in a K-experts. K, just assume the cache of capacity K, right? Where the files are the experts and you have to select a subset of K files at every round. What do you already know about this problem? So we actually worked on this problem earlier, and in our symmetrics and Newdip's paper, we actually showed that there is a lower bound. No policy can do in terms of just plain static regret guarantee, where you compare the reward obtained by your policy with the best reward obtained by the fixed caching configuration in hindsight. So this is a regret, and this regret cannot be lower bounded by square root of ct by 2 pi. This is we proved, and we also have an upper bound that shows that this bound is tight up to a factor of log n over c. But in our later work, we actually got rid of this lingering log n over c factor. So it is sort of tight, and it can be extended to network caching as well. So this is known. So, but as I said, so the regret metric there is kind of very weak in the sense it is only considering the best fixed subset of k files in hindsight. So you're just loading the cache with the best set of k files, and you are just keeping it same. You are not changing the caching configuration, and in that way you're getting this regret guarantee. So which is a very in my opinion, it's a very weak benchmark. So you in the ideal case, you'd also like your caching configuration to change, the offline optimal policy to change as time progresses, and this is what the problem we are looking at right now. So here, so this is our recent paper in ITW, and here we actually let the offline caching policy to be at every time it can change its caching configuration. The only constraint is that they are assumed that there exists a finite state machine, right? The number of states is finite, but there is no upper bound on the how many states it might contain, and the caching configuration at every time slot is decided by some function of the state that the machine is in to that policy, right? So this is only, so you can, so formally you can define it like this way. So you have a finite set of states in this set of file, and there is a transition function, and there is no restriction on the how this machine is evolving. But the only constant is that there is a fixed function f such that given any state, so it maps any state to a set of caching configuration. So as time progresses, of course, it travels over multiple states. So here is an example. This machine is actually as a different file requests comes, this machine actually traverses multiple states, and it can change its caching configuration on the go. The only constant is that the number of states is finite. That's it. And why is this sort of functions at this offline policies benchmarks are interesting? Because we showed that popular caching policies such as LRU and FIFO, which are known to be practical, they can also be described as finite state prefetchers. So they all fall in this class. So what is our objective? Our objective is to give you a regret guarantee which is competitive against a set of all finite state machines. So if you're looking at so RT of pi is the maximum reward obtained, that is the maximum cache hits obtained by any offline caching offline policy that looks at all these file requests and then just picks the best finite state machines in hindsight, and it gets a reward, and we are just comparing the reward accrued by our policy with this very strong benchmark. So the question is, can we design an algorithm that has a sublinear degree guarantee in this very strong setting? Okay, so as I said, so here, as I also indicate here in blue ink here, the benchmark section may change with time, and this benchmark is extremely strong. Now we show that some ideas from information theory that can be used for solving this problem. So here I'm not going to describe what the algorithm is. So the main idea is this: you first create a limpel zip parts tree, right? And the basic idea is as follows. So first we show that the reward obtained by any finite state machine can be approximated. I mean, in a strong mathematical inequality can be approximated by the reward obtained a very special class of finite state machines known as a Markov prefetchers, where Markov prefetchers is a finite state machines where your state is simply the past case symbol that you have seen. So this is how the prefetcher is done, and it can be shown that given enough number of this memory, any finite state machines can be approximated by this Markov prefetcher. This means that if we can emulate a Markov prefetcher in an online fashion and run an online policy at every node in this Markov prefetcher, then we'll be in a good shape. So this is what you actually show in this ITW paper. So the construction works as follows. So first, the LZ tree is initialized with a single with the root node and n leaves, and the current tree is used to create the next phrase by following the path from the root to leaf according to the request sequence. And you run a single instance of the online policy. For example, the previous Hedge policy or the FTRL policy at each node of this LZ tree, and that's it. And you just compute. This is your online policy. So you can see that as time progresses, the tree also grows. So the complexity of it grows sublinearly, but it grows. So it is not a non-uniform in terms of complexity. So the complexity also grows with time, but it has got a very good guarantee, very strong guarantee in terms of the regret metric. So here is just an example how this thing actually works. So you start with the limpel tree. So you start with empty tree, and then the first request 0 comes, and you just add a add a leaf there. The second request comes, you add a leaf there, and then in the next request you just follow the tree. And at every node, you run an instance of this finite any regret optimal policy that has a guarantee for the static regret only. Right. So this is the basic idea, and we show that this particular policy has a sublinear regret. It is definitely not as strong as square root of t. This is totally it is impossible to achieve. The regret grows like the normalized regret grows like 1 over square root of log t, which goes to 0 as t goes to infinity, but in a slower time scale. So, and what is the theoretical advantage of this? So previously it was not known whether there exists a policy that can simultaneously achieve a regret guarantee as well as a finite competitive ratio. So I'm not defining competitive ratio, what competitive ratios are, but I'm assuming that you have this knowledge like what competitive ratios are, but it is not known. But the same algorithm, since LRU and FIFO, they are in this finite state prefetchers, they're in the same class, our algorithm can guarantee both, and even much more, because it's just an instance of the finite state machines, right? So I think I have only 5 minutes. So again, so in this AI stats paper, we also fundamentally we have a characterization. So this is a sort of no free lunch theorem. What sort of loss profiles in terms of cache misses they are achievable? So we prove no free lunch like theorem. Of course, for all request sequences, you can't minimize the cache miss rate for all request sequences. If your cache miss rate is small for a typical request sequence, it is going to be large for some other request sequences. So this is the no free lunch. But what is the interesting point is that this can also be achieved for a sort of functions, the loss functions which we call a stable. Right. This also, it has got some connotations in this information theoretic literature. It was actually initially covered by Cover in 1960s. He actually considered this sort of problem for binary predictions, and we actually extend it to this NID caching problem setup. right? So there we assume that the loss function satisfies this sort of regularity probability, stability property given by equation 7 and 8, and we show that any function expected phi. So although we are taking expectation, there is no stochasticity assumed in the request sequence. So here is expectation simply the average over all this phi over all possible NID sequences. And if expectation of phi, the loss function is at least 1 minus k over in all phi functions which are stable in the sense of equation 7 and 8, they are achievable. So there exists an online caching policy which achieves this loss function, right? So with this, I would like to, there are some numerical experiments we did. So this is probably my last slide. And we showed that we actually compare for different sorts of loss functions. We considered the sum reward function in the first slide, in the first display, the pairwise reward function, where instead of looking at, so cache hit is when a single file is present, requested file. So in the pairwise reward function, let's say the user requests 2 files at any given time, and you get a reward of unity. Let's say an audio and video file related, and you get a reward of unity. Both the files are contained in this cache. So this is a pairwise reward function. This is a highly nonlinear function, right? And third display, we consider the max reward version of this problem, which is submodular. And in all the cases, we find that our policy. So there is, we also plot the lower bounds as well as the performance of some other policies. For example, LRDV and LFU. And some of the policies that we actually designed earlier in our sigmetrics and ISIT paper, and we showed that the proposed policy does pretty well, even in terms of numerical experiments with realistic data sets, for example, movie lens and image reality mapping sets. So with this, I'd like to conclude my talk, and here are some of these the reference papers that you can take a look at, and that's it. And let me know if there is any question. I'll be happy to answer. Yes, I see something on chat. Oh no. Okay.
Maybe I can begin with the first question.
Sure.
This is Rajesh here. So I want to understand the motivation for, I understand that when alpha is equal to 1, there are these submodular functions that you use, and therefore they have nice properties and you utilize them here.
Right.
What about smaller alpha? Where did they come? Could you explain?
Not a smaller alpha. We are actually looking at alpha equal to 1 is fine for us because this is covered by this things. We're looking at some alpha which is larger than 1. I mean, this is where this alpha admissibility is important, right? Because we see that so we are looking at this problem. This is the online sparse regression problem, and that particular the reward function that we actually considered, this is the R square reward. So this is simply the regression error that you actually get, or the R squared value, so the negative of that, and that particular function is not submodular.
Right. I'm just trying to understand the value that is, I mean, the utility of a larger alpha or a smaller alpha.
Yes.
So
it is given by this regret bounds. It's k over n alpha. So alpha appears at the bottom of this benchmark. So you definitely would like alpha to be small, if you can. So if you can find those GT vectors with small alpha, then it will help in your regret bound.
Okay, thank you.
So Abhishek, one question.
Yeah.
Even with alpha equal to 1, your regret is not same as the classical regret.
No.
Right, but have you done any experiments like how does the with respect to the classical definition, how does the
not yet
scale?
Numerical experiments? Okay, so the students are still doing it, and so our focus is more mostly on this right now on the theoretical part. But we see that there are lots of work that needs to be done on the numerical front. So we really have not explored the numerical aspects of this work. Yes, but what you are asking is it's extremely important. I mean, how the performance of the algorithm actually varies with alpha. I mean, the curvature of this function, but we have not explored it in detail yet, numerically.
Okay.
Any other question?
Yeah, just one question, Abhishek. So in this first term here, the one which you're calling benchmark, so that reward is always going to be bigger than the classical reward term,
yes,
right?
Yes. I mean, if you just considering that sum over ft of n, this is always going to be bigger than the classical, because the classical one is only going to choose k, right? The best k actions. And since I'm assuming ft to be monotone, I mean the sum of ft of n. So that's why it is much more stronger in that sense.
Right. Okay. Thank you.
Abhishek, can you flash your positive theorem? I mean,
which theorem?
I mean, the conditions under which.
Oh, yeah. You mean this one?
No, that is the LP dual for your definition of F, alpha admissible F.
Right. So you mean this lower bound?
Yeah. So what is the lower bound is you can't do better than.
Yeah.
Looking at the upper bound. So finally.
Oh, the upper bound. Okay. So this is the upper bound, right?
What are the assumptions on F? That it is
the
alpha
assumptions
admissible?
on F are simply you have it's alpha admissible. It is alpha admissible, and you assume that if it will be monotone. That's it. And so I'm hiding all these, these gradient conditions, the bounds on the gradient with this order, this big O notation. But assuming the set to be bounded, so yeah, so this depends on the gradient of the functions, and gradient meaning the discrete gradient of the function, and so on and so forth. But apart from this alpha admissibility, I'm not imposing any restriction on FT. And basically, we actually, I proved it. Why you don't need. So this is it. The proof is only these 3 lines.
Okay, so if alpha admissible, then you have that upper bound.
Yes.
Yeah. So can you explain why you restricted attention to alpha admissible F, in the sense that you of course probably arrived at it from one admissible submodular F and so on.
That is a motivation.
But why submodular F? Did you? I mean, you gave a bunch of examples in the beginning, but from there you leapt to a submodular function. So is there
I mean, we don't need submodularity. So submodularity is covered by one admissibility. So all submodular functions are one admissible. And here this is the theorem. This is known from 1971, theorem by Shapley. I mean, this is by definition sort of submodular functions are one admissible, right? But why we need alpha admissibility is that not all functions fall into this class that you are interested in. For example, the main motivation is that the sparse regression problem. So in the sparse regression problem, the function that the reward function that we actually, it is known by very recent work. This particular function is not submodular, and so it is actually alpha submodular.
Although for what alpha? For what
alpha? For what alpha? Okay, so this is depends on the norm of, I think, xt, some sup norm or one norm of this xt. So xt. So let me define. Go back to the definition of okay, where it is. Yeah. So if you're looking, so yes. So this is xt, right? So you're getting at every time you're getting xt, and that's the feature vector. And the submodularity, that alpha vector, the value of this alpha is related to some norm of this xt's. You stack them up, and then you take this probably take the 2 norm of that xt.
So you need all your xt's to be bounded in that norm, and that upper bound on this norm you can use.
That's true. That's true. Yeah, this is known. This is known from very recent works by Bill Mess. and also Sviddenko. There is a paper by Sviddenko, came up in last 2 years. So these functions known to be, so this is not the exact function that you actually need. So if you would like to do the sparse regression problem that we are solving, so online sparse regression problem, the function that appears in this online sparse regression problem, that particular function is not submodular, but it is alpha submodular. And this is why we need this extension. That motivated us to define this alpha submodular extension there. And it turns out that we can actually handle any alpha without any issue, because, and this is what the graceful degradation in the degrade bound that we have, that simply divided k over n alpha.
Okay, thank you.
Thank you. Any other question? So if you have any other question, just give me an email. You can send me an email in my official email ID, and I'll be happy to respond.
So if there are no more questions, let's end this session. Thank you, Professor Sinha, for an interesting talk. As discussed before, we would like to remind the audience to subscribe to our Google Groups, which is a mailing list for information on future talks. You can also visit our website for more details. The links have already been pasted in the chat box. The link to the recorded video will also be posted on the web page. Thank you and have a great evening.
Thank you.